Hello and welcome to part 2 of the video series 3D interactive visualizations. In previous part of this video series we talked about 3D plots using Plotly and specifically the express module of Plotly. We talked about scatter plots in there, and we also talked about 3D plots for classification data by reducing its dimensions by making different kind of pipelines and visualizing the discrimination in the data with respect to each class. And I also refer you to look into embedding projector in TensorBoard. That is very fascinating that's a very fascinating visualization tool for high dimensional data. When it reduced to low dimensional data for visualization, and there are certain algorithms that are there, and it has a very good interactive support to do that. In this particular part, we are going to talk about Decision surfaces. Particularly, the Decision surface is basically a surface that is there for a classification problem. For example, just think about you have a data set belonging to two different classes. Let's say binary classification problem. Maybe your classifier or the model at the end of the day assigns a positive score for one class and negative score for another class. Then the decision surface will be a surface that lies at the area where you are decisionless. So for example, if positive sign shows, let me show you that. So let's say you have this particular data just in 2 dimensions, 2 features, and let's say you have other data. Let's say this data, let's say all these data points. And let's say you want your model to produce positive score for these red points and negative score for these green points. Let's say there may be a curve which is sometimes called the decision boundary or decision surface or classification boundary, maybe like this. And this decision boundary has property that all the points on this boundary they are neither positive nor negative. So for example, if you have any point on this boundary, it is not positive, not negative. And normally for binary classification problems, this is some function of your features. Let's say in this case we have 2 features, let's say x1 and x2, and that is equal to 0 for 2 features. These decision surfaces or decision boundaries, they are relatively easy to plot for 2 dimensions or for 1 dimension or 2 dimensions, but sometimes it becomes really tricky to get the idea when you have 3 features and you have to plot a decision surface in the 3-dimensional space. For example, consider here we have 3 features. Feature X is a feature, Y is a feature, and Z is a feature. So let's say these are 3 features, X, Y, and Z. Assume you have a lot of data for X, Y, Z. Let's say X feature, Y feature, Z feature. Let's say you have a lot of data, and let's say you have a target label as well. Maybe it's a regression problem or maybe it's a classification problem. Let's say you have a lot of data for this. So you have this X feature value, this Y feature value, this Z feature value, and then whatever the target label. Assume, for example, classification problem, that's -1. Then you have another value, another value, another value. Assume the class label is 1. Another value, another value, another value, and class label is -1, and so on. Suppose you have fit a particular model, and the parameters of let's say the model you fit is looks like that. And this model, for example, if I write 2x square z square minus 2xy z plus 10z plus 4, this model gives a positive score. So this number stays positive for any feature that belongs to, let's say, class 1. And this score becomes negative if that sample belongs to class -1, let's say. Now you really want, what is the decision boundary? Obviously the decision boundary is where all the points where this model gives the value 0, because once the value is 0, it is neither in class 1 nor in class 0, so it will define a boundary between the two classes, if that's a classification problem. If that's a regression problem, then assume that this is the surface that is fitting all the data x, y, and z, where z might here be a target label, and you're fitting this data into that. So referring back to our classification problem, because that is more like easy to understand, the question is how can we plot this surface? How can we generate these points x, y, and z such that the result is 0? One way is to generate a lot of points on x and y. So let's say generate a lot of points on x and y. So let's say make a grid on x and y. So this is, let's say, x and this is y, and make a grid of it, just starting from somewhere and ending at somewhere. Let's say -2, -1, 0, and let's say 1 and 2, let's say 5 points. And then we have, let's say, -2, 1, 0, and let's say this is -2, -1, 0, and then 1 and 2. And all these points, if you plug in x and y pair, in place of x, if you apply the value, in place of y, if you apply the value, then the resulting function will be just having one variable z. For example, if x is 2 and y is 1, let's say, what will happen here? If I plug in x as 2 and y as 1, the result will be the following. 2 times x is 2, so 2 times 4, 2 times 4, then z square, minus 2 times 1 into z, plus 10z plus 4 is equal to 0, which eventually becomes 8z square minus 4z plus 10z plus 4 is equal to 0. So if I fix x is equal to 2 and y is equal to 1, then what should be the value of z that satisfies this equation? If we can find out such a value of z, then we'll be having one triple x, y, and z. Similarly, we can plug in another x, y pair and find out the corresponding value of z for that, and that will be another triple. If we have a lot of points that satisfy this equation, then we can plot these points, and that will be the decision surface. But now the problem is how to find out the roots of this particular function. There are numerical methods to find out the roots of this particular function, and now we are switching to Python to show you that how can we find that out. At the end of the day, this is a one variable function for which we are going to find out the roots, and there may be multiple roots depending upon the degree of or the shape of this function. We'll be using numerical methods from MP Math library, and we'll be finding out the roots one by one. We'll be finding out the roots for each xy pair that will generate, and we'll be having z values, and then we'll plot those, and that will count as a surface. So yeah, so let's go to our Jupyter notebook and get our hands fit onto that. So first let's say import some packages. So numpy as np, let's say, then import, let's say, plotly dot graph objs as go. So that is required. So let's import that. Maybe we import one more library, which is import. So from MP Math, we need this library for root finding. Import MP. So let's see if everything is fine. Yes. Now let's generate a grid of x and y pairs. First of all, let's see what is our let me type what is our polynomial. The polynomial is 2x square plus 2x square z square minus 2xyz plus 10z plus 4 is equal to 0. So that's our function. So this is our function, for example. So we should have our function in front of you, in front of us. So let's generate a grid by using np, np.meshGrid. np.meshGrid. So let's generate np.linspace, maybe starting from -2 ending at 2, generate for example 40 points maybe, or maybe more or less. Then generate another grid for y linspace, and let's say this is again -2 and 2, and generate 40 points. So yeah, so if you see now the shape of x and y, both shapes are 40 by 40. So these are 40 by 40 grid matrices. Yeah. Now, now let's generate the value of z that satisfy this equation. So we will pick values one by one from x and y. There are basically 40 such values. So we'll pick one by one these values, and what we'll be do basically 40 into 40 values, and we will plug in those values here, and then the result will be a function in z, and we will be finding out the roots of that function using this mpmath library. So let's do that. So what we do is the following. Let's say small x is x.flatten, and small y is, let's say, y.flatten, and let's define our small z that we really want to estimate. So let's fill this z now for I in range length of small x, these number of points, and let's define this zi is equal to float, because the return value of this mp.nstr is string mp. This mp, as you can see, this we have just this mp is, we have imported this mp from mpmath for finding out the roots. So mp.nstr, because the result that the root function returns is really in mp format, so we convert it to string and then we convert it to float. Then we call mp.findRoot, that function, and that function required for example a definition of the function that we really want to deploy. So for example, so lambda t is our, let's say, iterator variable for this particular function. And then what we do is we define this 2 hysteric x I, 2 hysteric xi square, 2 hysteric xi square, static t. Here t, think about this t as this z. So this t really is this z. This is the parameter of the final form of our. So this t square, that plus minus 2 hysteric x I hysteric yi hysteric t, and then plus 10 hysteric t plus 4. That is our basically that is our function. So if we plug in this x and y values inside, the function will only remain in t, or you can write as z here or whatever. That's our variable. Now we have to give this to this function. Now we have to give the initial starting point. So let's give np.random.rand. That's the initial starting point. These are numerical based methods, so they require starting points. We also have to give the tolerance value that we need the solution to be this much erroneous. If the tolerance value is small, you'll be finding out more accurate solutions. If tolerance value is large, then you may be finding out some errors in there. But depending upon the solver, the default solver here is secant method. There may be others. There are other solvers as well. This tolerance value can be varied and stuff like so. And sometimes the tolerance value is set in a way that it cannot find out the root with respect to that tolerance. That's why I'm setting the tolerance to be a relatively loose value. So that is our zi. Now what we do is we append this z. So z dot append with this zi, and that's it. So with this, after doing that, we'll be having our x, y, and z that are available according to the root. Now xy grid, we already have xy grid available, and now we find out the value of z by plugging in each value of x and y, each pair of x and y, we find out the value of z that satisfies this equation. Now we have x, y, and z again back. So let's convert this z to np dot array, this z dot reshape. How many points do we have? What's the shape? That's 40 by 40. So let's reshape into as a grid. And now after that, we are ready to plot our decision surface. So let's plot our decision surface. Figure is equal to go graphic object figure data is equal to go dot surface where x is equal to capital X, y is equal to capital Y, and small z, which are the argument, is equal to capital Z. So that's our surface. If there is no error, it should run fig.show, and if we just run that, if it runs properly, then we'll be having a surface to show. Yeah, so this is the surface. Yeah, cool. That's the surface. These are the different values of x, y, and z. So yeah, so you can play with that surface. You might be noticing that the surface is very noisy, although the input function was smooth and it was kind of very smooth function, so it could not. By the way, this root finder is just an approximation, and depending upon the tolerance, it may have found the roots that are not very accurate, but that's one kind of. So we can just, for example, again, we can zoom out, we can zoom in, and stuff like so. And in several cases, when we have to draw these decision surfaces, for example, given a function. And by the way, this find root function does not only care about finding the roots of polynomials. You can have any complicated kind of function, and it will approximate the roots. This mpmath library will approximate the roots for you, and you can find out the decision surface as long as your features are 3 or 2 or just 1. Obviously, for more than 3 features, we do not have direct visualizations that are available. But sometimes I find really hard for people to actually draw even for 3 features, even for 3-dimensional space. People find it hard to find out to draw these decision surfaces. Now think about some data points that are here that belong to class 1, and some data points below here that belongs to class -1, and that is the boundary between those two classes. Yeah. So that's about decision surfaces in Plotly. In the next video, in the next part of this video, we'll be focusing on plotting multiple surfaces and scatter plots just in a single plot. So that lecture or that video, that part will more primarily be based on plotting multiple surfaces and multiple scatter plots in a single plot using this Plotly. So yeah, hope to see you in the next video.